Okay, so for chapter 2, we need we're looking at the second law of thermodynamics. So we need to study how systems usually store energy, and we have to learn and give some idea on all the various ways that an energy can be arranged. Now, the mathematics that deals with this kind of um, arrangement or count is called the combinatorics, and I will explain some of the fundamental ideas of combinatorics here in this recording, and I will derive the general formula that you've all have heard of. If we have n objects and we choose, let's say, a certain number of them, how does that work? Okay, so I'll start with very general example. Let's say I have 3 coins, and I flip them. Okay, and how many possible outcomes do I have? Well, let's make a table to show the outcomes. So there's coin 1, 2, and 3. Well, so there's 2 faces on each coin, the heads and the tails. So the first possibility is that I get heads on all these coins, so they'll all be heads. That's one way. Another way is I could get heads on the first 2 and a tail on the other. And then the second possibility, I could get heads on the first and last and tails in the middle. And then I could keep on going and listing all the possibilities. And if I do that, I have I could get tail here, head, head. I could get head, tail, tail. I could get tail, head, tail, 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 head, and they all could be tails. Tail, tail, tail. Okay, so these are all the possibilities. These are all the outcomes that I can see in the various ways of flipping these coins. Now, there's a total of 8 different ways, right? If you count 1, 2, 3, 4, 5, 6, 7, 8. So there's a total of 8. So now we can ask, what is the probability of getting 3 heads? 3 heads. You could see that the probability of getting 3 heads or 3 tails is 1 out of the 8. So the probability of getting 3 heads is 3 heads, 3h, is equal 1 out of the total out of 8. Okay, we could ask, what's the probability of getting 2 heads? The probability of getting 2 heads, we can count the cases that have 2 heads, and we could see that there's 3 cases that have heads out of 8. So that's 3 out of 8. And so on, of course, assuming that the dice are fair and each outcome is equally probable. Okay, now each of these 8 different outcomes is called a microstate, because that tells me exactly what each coin's representation is. I know exactly, like for example, on microstate number 1, I know that or let's take microstate number 2, I know that the first coin landed heads, the second coin landed heads, and the third coin landed tails. So this is called a microstate, which means I am specifying the state of each individual coin. So that's labeled as a microstate. Whereas if I in general say how many heads or tails are there, this is more of a macrostate. So for example, if I say the scenario with 2 heads, that's a macrostate, because I know that the second throw gave me 2 heads, the fourth throw gave me 2 heads, but I'm not sure which one of the coins was the tails. So That means I'm being more general here. I'm not revealing the microstate of each particle of each coin. However, I am revealing the general state being two heads and one tail. So that leads to a conclusion that if I know the microstate, I definitely know the macrostate, because the microstate is much more specific. It's giving you the entire story, and from that you can reference the macrostate. However, if I know the macrostate, that doesn't necessarily mean I know the microstate, because knowing that I have two heads and one tail does not tell me which one of these two coins has the two heads and which one has the third tail. Okay, so that's the story with microstates and macrostates. Now, the number of microstates corresponding to a given macrostate is called the multiplicity of the macrostate. Okay, and they use in this book for the multiplicity the letter omega, Greek letter omega, that corresponds to the multiplicity of the macrostate. Okay, so let's say, for example, if I want the multiplicity of getting 3 heads, right? 3 heads. Well, there's only one way I can get 3 heads, and that's the first one, the one when they're all 3. So this would be a 1. Whereas if I need the multiplicity of getting 2 heads, well, coin number 1 and coin number 2 could be 2 heads, or so this is 1 here. Coin number 1 and coin number 3 could be 2 heads, and coin number 2 and coin number 3 could be 2 heads. Any others? No, the rest don't have 2 heads. So that means I have a total of 3. So this would be 3. Okay, and so on. Now, what about the multiplicity of getting 0 heads? Well, this is only the place where we got tails, the last one, which is only 1. Okay. So now, what is the total multiplicity? The total multiplicity is actually getting all the 4 macrostates. I have 4 macrostates in this problem. And that would be, so the multiplicity of all, let's write it down here, right? All heads is 1, all tails is 1. I could get 2 heads and 3 heads and 1 tail. 2 heads and 1 tail, we already said this is 3. Or we can have 2 tails and 1 head, that's also 3, right? The rest are just variations, but the multiplicity is the same. So there's a total number of 8, but there's all in all there's 4 macrostates. The general specification of the system in terms of how many heads and how many tails. So this gets me 8. Okay, now the probability of any particular macrostate then would be the multiplicity of that specific macrostate divided by the multiplicity of all the states. So let's write that down. This is important. So if I'm trying to find the probability of getting n heads, for example, this would be the multiplicity of getting n heads in whatever microstate the system would allow it to, divided by the total number of multiplicities on all of them. So for example, let's do an example on this. Suppose that I want to find the probability of getting 2 heads. Okay, so the probability of getting 2 heads, I'll call the probability P, by the way. Probability. Okay, so let's say I want the probability of getting 2 heads. So this would be the multiplicity of getting 2 heads, which we discussed above, divided by the multiplicity of all. Okay, and we already said that to get 2 heads, there's three ways you can there's three of the microstates reveal 2 heads over 8. So this would be 3 over 8. Okay, assuming that all the microstates are equally probable. Now let's elevate this argument a bit to further coins, and let's say instead of having 3 coins, let's say that now we have 100 coins, and let's see how this thing generalizes. So if I have 100 coins, okay, what's the total number of microstates? Well, think about it. Each one of the coins will either be head or will be tail. So the first coin has 2 microstates, being either head or tail. The second coin, the same story, either heads or tails. And every coin afterwards will have 2 microstates, either heads or tails. So I could keep multiplying 2's all the way 100 times. So this is the 100th 2. This is the 100th 2. So in brief, then, the total number of microstates, so microstates, right, will be, for 100 coins, will be 2 to the 100. 2 to the 100. Okay, now the what about the number of macrostates? Well, the macrostates more generally, it's a little bit different, because what do I have? Well, I have so there's 100 coins, so they could either be heads or tails. So I could have, so on the first coin I could have either heads, I could have 0 heads, so all of them would be tails. That's one way. I could have 1 head and 99 tails. So 1 head, right? So here I'm specifying the macrostate without giving any particular importance to which of the coins is actually the one that is landing heads. All I care about is how many heads out of all the coins. So I either get 0 heads, I get 1 head, I get 2 heads, I get 3 heads, and so on all the way to 100 heads. And if you count these cases, including the 0 heads, where everything is tails, you have 101 microstates, macrostates. So the macrostates, for this example, the macrostates is 101. Okay, now let's discuss the multiplicities of these macrostates. So we know we have 101 macrostates. Let's talk about some of their multiplicities. Let's start with the 0 heads microstate. So 0 head macrostate. Right? Well, if there's 0 heads, that means every coin is tails. So you've already specified the microstate of the system. So that means the multiplicity of 0 will just be 1. Right? Because the exact microstate has been specified. Okay? Now, what is if there is 1 head macrostate? Right? So there's only one way to get a 0 heads, is if everything else is tails, and therefore the multiplicity is just 1. There's only one way to do it. Now, if there's 1 head, however, right? The heads coin, the heads up coin, could be the first coin. It could be the second coin, it could be the third coin, and then you can count all the way up to 100. So so there's exactly 100 possible ways where you could get one-head macrostates, because any of the 100 coins can actually adopt the one-head configuration, and therefore the multiplicity of one head will be 100. Okay, now by the way, another way to look at this is that if you imagine all the coins are starting heads down, then the multiplicity of one head is how many ways of choosing one of them turning down, flipping the other way. Okay, now let's go to the multiplicity of two heads, right? Macrostate. Right? Now, well, think about it. If I want two heads out of the 100, I could have one head. So I have 100 choices on the first coin, on the first head, right? So that's 100, right? And equally likely, not equally likely, one less likely, 99 coins, because I already counted. The first one will be one of the 100, so it's already been counted. Now the second head would be one of the remaining 99. So this would be 100 times 99. But since I could pair this either way, I could start, I've double counted here, of course, because 100 times 99, that would count starting with the two head from either way, because if I'm starting one head on the 100, that means by the time I'm done, I would have double counted, because I'm also counting 99 others on the second head. So I would have to divide this by 2. Okay? So you have 100 choices on the first coin, right? And each one of these choices, you have 99 remaining choices for the second coin. But again, you could choose any pair in either order. So the number of distinct pairs would be 100 times 99 over 2, and this would give us the multiplicity of 2. Now, let's generalize this argument. Actually, let's do the 3, then we'll generalize this argument to the fundamental theorem of combinatorics, or the formula of combinatorics. Let's say I want 3 heads macrostate, right? By the same exact reasoning, right? I have 100 choices on the first. I have 99 choices on the second, because in one of them I would have already counted, because everybody in the first count is heads up. So that would be 99 on the second, and then I would have 98 on the third, and of course all these are multiplied by each other. Okay, but then this triplet could be chosen in several ways, right? There's 3 choices for which to flip first, and for each of these there's 2 choices for which to flip second. So there's technically 6 different ways of doing this. And if there's 6 different ways of doing this, that's just saying 3 times 2. Okay, now if you look at 1-head macrostate, 2-head macrostate, and 3-head macrostate, you can easily see how this generalizes. And now let's say we're gonna get the multiplicity of n, right? You can see that if I have 100 coins, right, I'm multiplying 100 times 99 times 98, right, all the way short. So here, to get to 100, I have 2, right, but I have 3 heads. So that means I'm exceeding, I'm going 1 lower. So the difference between 100 and 98, which is 2, you can see that the difference between the first and the last is 2, which is 1 less the number of heads. Okay, so if the number of heads is n, right, this would be 100. So I'm going to multiply all the way through by 100 minus, right, n plus 1, n minus 1. So the last number has to be 1 less than the number of heads, which in this case is n, over. Now you can see that on the 2 heads there's 2 in the denominator. On the 3 heads the number of different ways became 6. That's 3 times 2, right? So this is just 3 factorial here. On 4 it's going to be 12 different ways, sorry, 24 different ways, 3 times 4 times 2. And so when I get to n heads, this is going to become n factorial. Because it's going to be, let me write this down first. It's going to be n times n minus 1 times n minus 2 all the way to 1. Okay, this denominator, this is called n factorial, which means you're multiplying all the numbers up to n. Okay, if I briefly simplify this, I can get psi n to equal, this is 100 times 99, right, all the way to 100 minus n plus 1 all over n factorial. And now what I'm gonna do to just make this look nicer, I know that I'm multiplying here all the way to 100 minus n plus 1. What I could do, I could multiply, so this is technically, if I were to say this is the same, except to make it 100 factorial, right, on top, which is the number of coins, the total number of coins, I would have to add, because this is minus n plus 1, I would have to do times 100, so this is 100 minus n minus 1, I would have to do times 100 plus n, minus n minus 1, 100 minus n plus 1, and then the one after will become 100 minus n, right, over 100 minus n. Yeah, it's actually easier to see this one if you look at the example on the 3. Now notice here, if I were to make the numerator 100, right, that would multiply all the numbers down to 100, but my numbers only go to 98, so I would have to subtract from the 100 the last 97 numbers. So that's 97 times 96, etc., etc. So if I divide by 97 factorial, which would be the 100 minus 3, I would have eliminated that difference. In other words, what I could do here, I could write this as 100 factorial, right? Just to show you how I'm going to arrive to the general form. This is 100 factorial, which would be 100 times 99 times 98 times 97 all the way down to 1. However, in my numerator, I only have the first 3. I don't have the rest. So what I could do, I could say, okay, well, fine, 100 factorial, and then I can further divide that by 97 factorial. And what this 97 factorial is, it represents all these numbers here, and then I'm able to just cross them out, and if I cross them out, I would get back to my actual numerator, which is 100 times 99 times 98. And what was this 97? This 97 was the number of coins minus my macrostate, minus 3 factorial. So in this case, it's gonna be, I'm gonna make this 100 factorial, and I'm gonna divide by 100 minus n, because now my number of heads macrostates is n. So this would be 100 minus n factorial times n factorial. So and this is what you've heard of before, spoken as 100 choose n, the number of different ways of choosing n items out of the 100, or the number of combinations of n items chosen from 100. So now finally, to generalize this fully, if there are n coins, so to summarize, if there are n coins, right, then the multiplicity of a macrostate with small n heads, let's use this, then the multiplicity of macrostates with n heads will be the number of coins n factorial divided by heads, and then number of coins minus the macrostate heads, all factorial. And this is what you usually hear when they say n choose small n. The number of ways of choosing n objects, small n objects out of n items. And I hope that this discussion further points you to the right derivation of this formula without actually having to memorize it, but rather to reason it out and make sense of it. So you can derive it anytime you forget it. That's what physics is all about, after all, is not so much use the formulas, but rather have the insight and the ability to derive them whenever are needed or whenever new derivations require it.